Okay, in this lecture, I'm going to talk about the divergence theorem. So this is the last theorem in the series of 3 theorems. So in the previous several lectures, I talked about the Green theorem, the Stokes theorem, and this is the last theorem called divergence theorem. So divergence theorem talks about the relationship between two types of integrals, which are the triple integral and the surface integral. Okay, before talking about the details, let me go through some of the definition notations used in the divergence theorem. So since we talk about the relationship between the triple integral and the surface integral, let's talk about the setup of this theorem. So we're talking about 3D. Here for the divergence theorem, we're talking about a 3D, a compact 3D space with piecewise smooth boundaries S. So as shown in this figure, we have a 3D. This is my 3D object. Is a compact, which means it doesn't go to infinity, and also with a piecewise smooth boundary S, which means it has some boundaries over here. As this is the top boundaries, the bottom boundaries, and left and right boundaries, all front and back. Okay, boundaries. Okay. So the boundaries are smooth, meaning that as a piecewise smooth means you could have like the corners, for example. But this is smooth from the top or the bottom, for example, here in front and back, and left and right. They are all smooth, which means you can take a derivative. Okay. Also, we have let f x y z be a continuous differentiable field. So this is represented by f. Okay, this is my f, x, and y, and z, which is a continuous differential field, which means for any point. Of course, inside here, point, I can define there's a vector associated with that point. It's called a vector field. Okay, but this is continuous differentiable, which means I can do a partial f over partial x, partial f over partial y, partial f over partial z. They do exist, so that's called partial continuous differentiable. Okay, if that's true, then we can say the triple integral of this is called you can see this as divergence. Okay, computer divergence. The divergence of the vector field. So this is given by partial f1 over partial x, partial f2 over partial y, plus partial f3 over partial z, assuming that my f vector is f1 x, y, and z, and f2 x, y, z, and f3 x, y, z. Okay, so this is my fx. You just take a partial derivative and you compute the sum. So this is basically the divergence. Okay. Now this is the integration of the divergence over this 3D object is the same as integration over a surface, which is a surface. This S is a boundary. So the boundary, which means including the top and bottom, left and right, front and back. So this is a whole entire boundary. Is the same entire boundary of f, this vector field dot product n and vector times d sigma. You do the surface integral. So here n is the outward pointing unit normal at each point on the boundary, which means if n, for example, this is what it shows about n vector. Okay, so this is n vector here, which basically means for any point you want to find you basically have a tangent surface, and for this point you compute the vector, unit vector that is perpendicular to the tangent vector of a tangent surface of the boundary on the boundary. So you compute that. So basically here you're going to point here, this is going to point here, this is going to point here, just perpendicular to the tangent surface. Okay, then for the boundary. Okay, so that's called n vector. This is n vector. First of all, it has to pointing outside, pointing outward. So there are two vectors. You could point it inside or outside. So we're not talking about this one going down. We're not talking about this one going down. It's pointing outside, and also it's unit vector. All right. So that's the meaning of this. That's what is the the divergence theorem says. It just says that the trivial integral of the divergence is the surface integral over the entire surface of the boundaries of the 3D compact 3D space of f dot n over the surface. Okay, integrating over the surface. Okay, so what is the physical meaning of the divergence theorem? There are some physical meaning of divergence theorem. Well, this says, if you look at this integration, this two, okay, separately, okay, this guy, the integration of this guy is you basically compute the divergence over the entire 3D space that you were talking about. So basically it says, hey, I'm going to talk about divergence every point here, 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 every point here, okay. I talk about divergence. Divergence basically means you get more particles coming in, assuming that my vector field defines the velocity of the particles in the field. So you're talking about how many particles coming in and how many particles coming out, basically, okay. So as you can imagine, the accumulated divergence of the field, but the inside one they all cancel out, because if you inside one, you're going from here, you're going to your neighbor one, right? One of the neighbors here, right? Any particle coming from here will go to the neighbor one. Unless it goes to the boundary, it can become coming out. It become moving out. Okay, that's why it is equal to this guy. This guy called accumulated divergence over the surface of S. So because this n is called outside, if I do this one, say, if my vector field, if my vector field at this point, okay, is pointing right, okay, because this n also pointed out, so this, which means the particles were moving out. If the particle, the surface, the vector is pointing in, for example, for this one, so which means at this point you have particles coming in. Okay, so basically what it says, the accumulated divergence over a 3D region V is the same as the accumulated divergence over the surface of the region. Surface of V. This should be V. The surface of V. Because all inside divergence will all cancel out. This means all inside divergence will cancel out. Let's see, that's why they are the same. Okay, now I'm going to show you one example about how we use the divergence theorem to sort of simplify the computations. A lot of times we're doing the opposite. We're trying to, because this one can be hard. If you look at this one, if you want to compute the surface of the surface integral of this guy, you have to compute the surface at top, bottom, left, and right, front, and back. So typically this is hard to compute. This is you have even if we can compute for each one, we can do this one include the top. For the example over here is the top, bottom, left, right. What I mean is surfaces and front and back surfaces. So you can do that. You can compute 6 individually, and you compute the sum of those. So this can be really difficult. In general, can be time consuming. Now if you do use this one, can be a little bit easy. Okay. Now I'm going to show you example how we do that. Okay. The exercise, the problem I'm talking about is we want to use a divergence theorem to compute this surface integral, okay? And this surface integral S is determined by what? So n, of course, is defined as I mentioned before is outward pointing unit norm at each point on the boundary of the surface. Okay, F is given by this. This is my F, and this n is defined in the theorem. Divergence theorem, following the definition of divergence theorem. Okay, and here my S is the boundary of this. I draw it over here. Is boundary of this cylinder. Basically, the cylinder. The cylinder is described by this. It's actually though its cylinder is the center of the cylinder is a z-axis. And the radius of the cylinder center, radius here is 2, which means x squared plus y squared is 4. And also z is bottom is z when z is negative 1, and the top is when z is 2. So you start here. You basically have cutting a cylinder centered at the z-axis and with radius 2, and starting from the bottom at 1z is -1, and the top is 1z is 2. That's my cylinder. So this S is the surface of the cylinder, so including the top and bottom and the side. Basically, the side is almost the entire surface on the side. Okay, so that's my surface. So basically, if I want to compute this one, if I want to compute this directly, the sigma, I have to compute 3, 1, S1. So S1 is top, F d sigma plus S2, F and d sigma plus S3, F and d sigma. So you have 3 of this one. You can do each individual one, and do the parametric representation, compute the n, then you compute all the stuff. It's rather complicated. Now I'm going to show you how to use divergence theorem to compute this one in a fairly easy way. Okay. All right. So if we use divergence theorem, so what we can do is, according to the divergence theorem, this integration is the same as a triple integral of the divergence of f dx dy dz over the 3D. Of course, this is over the cylinder defined here. Okay, this is a triple integral. So if let's do some computation over here. So before I talk about lower bound, how to figure out lower bound, because I have to compute the triple integral. Okay, I want to figure out what is the gradient of f, the divergence. The divergence f is defined by here is cosine y is cosine y. So it's partial cosine y over partial x plus partial sine x over partial y plus partial cosine z over partial z. If you do that one, this guy is 0. This guy is gone because this is 0. This is 0. So you only have this guy. This guy is just negative sine z. So this one becomes just the triple integral of sine z over the cylinder. Okay. Now let me redraw the cylinder over here. This is, I copy the cylinder over here. So I want to figure the lower bound, upper bound for the dx, dy, dz before we can compute the integrals. Okay. So as I mentioned in the previous lecture, okay, if you don't know how to do the lower bound, upper bound for triple integral, you can check my previous video. So on the triple integral, so basically start with one for z, for the very outside one, the z one. Okay, the z is you basically see for this cylinder. In order to fully find the cylinder, what is the lower bound of z I can find, what's the upper bound for z I can find. Apparently, you start from -1 to 2, because below -1, nothing. It's not a cylinder is not defined there. About these two, so no cylinder is defined about that. So you basically say this is my lower bound, upper bound. So finally we're done with z. Now for x and y, okay, dx dy, if we for any z, this one, once we figure this one, we say, hey, for some z over here, so what is my x and y? What is the area I'm going to do, right? Basically, what is the area I should integrate for x and y? You basically have this. You sort of have, you know, it's a circle, right? It's a circle because that's a cylinder, okay? Now, when you do that one, if you draw this one for any s, it doesn't matter what, any z, doesn't whatever z you've selected. So it's always a circle over here, right? It's always a circle. The circle has a radius of 2. It doesn't matter. That's not depending on z. So this circle is this. So just centered at 0, x or y 0, and your radius 2, basically, right? So if I do this one, if you integrate a y, so you want to figure out, hey, what is my y should be, lower bound for and upper bound for y. Apparently my y I can select, for y I can select from here to here, basically, right? From here to here. So let me do this one, okay. From here to here, so y I can select it from -2 to +2. That's why I have from -2 to +2. So lastly for x, what I do is I select a y. I select certain y. So let's see, I select a y somehow over here. Let's say I do some y. This is my y. If for my y is fixed y, means I go here and here. Remember here, this is the axis, this is y axis. Don't be confused about it. This is not an x, okay? So this is y. This is certain y. What is the lower bound for upper bound for y? So here, because this one, if I do this one, so this is a circle. So this is radius is 2, and this is 90 degrees for over here. So, and this is, of course, this is a y, some y value. So this value for x will be just, this is the upper bound, right? The upper bound will be just square root of 2 squared minus y squared, because this is a triangle. Okay, so this is 2 squared minus y squared. This is this squared. You take a square root, is what the x will have. This will be directly negative square root 2 squared minus y squared. Okay, so that's why I have here is negative square root of 2 squared minus y squared. This is positive square root of 2 squared minus y squared over here. So here we figured out what's the lower bound, upper bound, lower bound, upper bound, lower bound for x, y, and z. Okay. Now we just have to compute the integrations. Okay. So here's how we do it. Okay. If you do the integration over here, so if you do integration for this triple integral, so we could start with the first one. We could start from the inside one. Right? Could start with over dx, but I choose to move this one sin z outside because this is a constant. If you can see, this is a constant. It's not a function of x. So we can move it outside over here. So for I don't integrate it right now. Let's show you why we don't do that. If I do it over here, then we move it outside again. So because this one again, this is not a. When you do the integration here, you get a function of y. So this one we know. This is some function y, okay, and this guy is also not a function of y, right? So we can further pull this one outside here, okay. Then you only leave it here. The reason I'm doing this because here I don't want to do the integration because if I only have one over here, if I pull it out, I have just one over here. So I integrate this one over dx dy over this region basically. This region again defined by this right over here. So this is just the areas of this, the size of this area. So I don't have to do integration individually, one step by step. You can do it, of course, if you want to, but if you only simplify this way, you just have areas s, which is just pi, because the radius 2, so the size area is just pi times 2 squared. Okay. So once you do that, so you do is negative sin z. You do negative sin z over here. You still keep it over here. Then it's pi 2 squared. It's 4 pi. And I move this negative outside and pi 4 pi outside, so the integration becomes integration from negative 1 to 2. That's the region for z and sine z. Okay, so this one, because this is the sine z, the integration of sine z is negative cosine z, right? And these also have negative sign, so it cancel out. Become 4 pi cosine z and evaluate from 2 and negative 1 to 2. Which will be 4 pi cosine 2 minus cosine. This one has to be negative 1, right? Because cosine negative 1 is also cosine 1. So it's 4 pi of cosine 2 minus cosine 1. So that's my the final result. So if you look at this one, I don't have to do all the computations I'm supposed to do if I just compute it. If I want to compute it directly, okay, it becomes really complicated. But if I do use the divergence theorem, it ends up pretty fairly easy to compute out the solution. I don't have to divide into 3 terms, just one term be done. Okay, that's the beauty of the divergence theorem. So this also applies to the Green's theorem and the Stokes theorem. So a lot of times they can help us simplify the computation.